Okay, we can restart the session. Now we will have Paolo Gorla that will talk about solid-state detectors, in particular of cryogenic detectors. Paolo is a researcher here at LNGS and he is very expert in cryogenic detectors. He is presently the technical coordinator of the CREST experiment and of the Quarry experiment that are both using this technology.
Okay. Thank you, Carlo. Okay, so I will try to go a little bit into the physics of cryogenic detectors, and just at the end there will be a short set of hints of which kind of physics process you can study with this kind of detectors. So in the first part, which is the main part of the lecture, there will be the discussion of the working principle of the techniques and the sensor that are needed for this kind of detector and the specific background and features you can explore with this detector. So let's go through this one. So first of all, cryogenic detectors, which are sometimes called bolometers or low temperature detectors, are detectors that are designed to be ideal calorimeters, so in which basically 100% the full release of energy is measured. And yeah, this, for those who are familiar with ancient Greek, the name bolometers comes, it's just radiation detector, ray detector. The working principle is very simple. The basic idea is to measure the energy deposited by an impinging particle into a calorimeter, an absorber material, as it is converted into heat through a temperature sensor. So the real detector is composed by an energy absorber in which the radiation interacts and produces a temperature increase, and by a temperature sensor that reads this increase. In some specific application, you can skip, let's say, the energy absorber being the temperature sensor itself, the energy absorber. So the radiation interacts directly in the device, which is actually measuring the temperature rise. Just a very short historical note. The use of cryogenic detector in elementary particle physics goes back to the 1970s, but the real step ahead came in 1984. So these two guys, Ettore Fiorini from University of Milano and Tapioni-Nikoski from CERN, they published this work here. This is the preprint of the paper, published originally as a preprint of CERN, in which they proposed to use cryogenic calorimeters as a single radiation detector, so to detect the energy of the single interaction, not as a measure of the integrated energy as was used before. The actual story I was told by Ettore was that he was in CERN for different business, and Tapioni-Nikoski was characterizing very low temperature resistors, and he found a lot of spikes into this resistor. So in a lunch discussion, Ettore made a rough calculation and estimate that the number of spikes was proportional to the expected flow of cosmic rays. So they had the understanding that he was seeing in this resistor the passing through of muons from cosmic rays. And from this lunch discussion, they had this idea. And in the following years, especially in the 90s, the field underwent a huge development. Actually, around 80% 1984, there were other groups proposing similar ideas and proposing to use these detectors to study different processes. In particular, Ettore was focused on increasing the sensitivity of neutrino-less double beta decay studies. But in the 90s, there was a huge development of the cryogenic detector community, boosted especially by neutrino-less double beta decay and dark matter search. And nowadays, cryogenic detectors have found a real large set of fields in which they are extremely useful and then can bring very exciting results. Yeah, maybe, of course, I mean, there is no perfect detector, right? Whatever is the process you have here in these days, completely different techniques and technologies. Whenever you start to search for some physics process, you have to find the ideal detector or the detector which is the best compromise for the process you're looking for. So now I will show some of the features of this detector and some of the fields in which cryogenic detectors are extremely effective, while as you have heard about large liquid scintillators of cryogenic liquids, which can find much suitable application in other type of physics processes. Characteristic of this detector. This, as I said before, are detectors are sensitive to the single individual radiation interaction. This is very typical in many particle detectors, but it was not the application of cryogenic detectors before the 90s. And the detection is mediated by elementary excitation in a solid, which are basically lattice oscillations, so phonons. And the excitation energy of phonons in the lattice of a solid material is extremely low, in the few millielectron volt scale. So one characteristic that is very important is that to measure such energy, you have to be far away from thermal excitation that generate many of these energy carriers. So in some way, low temperatures are needed. And as we will see before, extremely low temperatures are needed, which is in some way one of the challenge of this kind of technology. A specific part of the detector is dedicated to the detection of the excitation produced by the particle interaction. And this is the part, the sensor is the part which has the real technological content. The absorber can be basically, under some condition, any kind of solid material, sometimes even liquid material, but let's say any kind of solid material. But the sensor is the real technological part in which you have to provide some device that is capable to measure extremely small temperature rises. And of course, this is the part which sets in some way or has a relevant impact on the signal-to-noise ratio. And as I said, it can be sometimes also the full detector. The interaction can happen directly in this kind of device. And there are, in principle, several information that you can extract. Some of these are actually extremely challenging to extract, but let's say the most relevant, which are easy to extract and which are the boost of this technology, are the energy, so a very precise measurement of the energy, and the time of the event. But in principle, you can, under some condition, measure also the type of impinging radiation, the position of interaction, and so on. But the real feature that are offered by this detector is, of course, the time and the energy. Also about the time, there is some discussion that need to be made. So first of all, the crucial part of this detector, the reason why this detector was developed, is that they offer an extremely good energy resolution. And the reason of this is, first of all, the fact that the energy of the carrier is extremely small. So the intrinsic broadening of the physics process of the line that you are measuring, of the energy of the reaction, is strongly suppressed by the fact that the energy of the carrier is extremely small. So when you look at the enlargement of the energy due to the square root of the energy of the number of the carriers, this give you an extremely small number, and this is why you get immediately in some way an extremely good energy resolution. This, of course, under ideal condition in which you are just dominated by this effect. In real detectors, you have many contributions to the energy, and you end up with a final energy that is still extremely good, but is far away from the theoretical limit of the Poissonian fluctuation of the number of carriers. Anyway, if you look at the typical energy range of most used detectors, so the energy of the scintillation phonons, the carrier in the gaseous detectors or in the solid state, in the semiconductors in some way, compared to the one of cryogenic detectors, it's extremely small. So you have an immediate gain on this, and the other real advantage is the fact that in most of this detector, the energy that actually converts into a signal that you can measure is a small fraction of the actual energy of the interacting particle. Most of the energy converts into processes that are either extremely long or to which you are blind in your detector. The typical channel is the phonon excitation. In solid material, most of the energy of the interacting radiation is converted into excitation of the oscillatory modes of the crystal, of the material that you are using as an absorber. So you lose most of the energy. So in best scintillator, for example, in solid material, you have that some 15% is converted into actual light signal of the deposited energy. And so if you can move this number to from 15 to 100%, you have another immediate gain of this technology that tells you why it's interesting to work with this kind of detector. There used to be two main, let's say, families of this low energy detectors. The one in which the energy is converted immediately into phonons, so the electric materials or semiconductors in some way, and the superconducting materials in which the interaction produce what is called quasi-particles, so the breaking of the Cooper pairs inside the semiconductor. Actually, I will focus on what we call phonon-mediated particle detectors, in which the signal is, the released energy is converted into lattice excitation of the lattice oscillatory mode of an absorber material. This in some way also tells you that the kind of material which are better or best for this kind of application are those which a very nice or good crystalline lattice that allow very good propagation of phonons and easily detection of this material. Amorphous material or are more difficult to use because the propagation of phonons is much less efficient, even though you can use also this kind of material. So phonon-mediated particle detector, the interaction of the radiation deposit energy into the absorber and generate this kind of excitation, the phonons. And you have an original distribution of phonons which really depends on the kind of interaction mechanism, of the kind of radiation that's that is interacting. So you expect different kind of phonon spectra depending on the kind of particle, especially differing between ionizing and non-ionizing particle. But actually, it's very difficult to be sensitive to this kind of distribution because it's prompt during the interaction, and typically sensors are much, much slower than this. And in fact, the phonons produced initially are out of equilibrium. They are thermal phonons, but going on in time, they propagate and they reduce their energy. So originally you have this high energy phonons. These are called often ballistic phonons that propagate through the material, and then through a number of processes, they degrade their energy. Typical reason to that boost the degradation of the energy of phonons are impurity in the material, reflection to the surface, and other kind of aspects that in some way induce. This is a sketch of how this happens. This is actually the crystal bands. This kind of sketch is built with a two-dimensional model, so it's not the real distribution of the crystal bands is a complex 3D object, which is difficult to visualize. But in this simplified model, you have this original generation of thermal phonons, which is in the optical branch, and this kind of phonons eventually reflect or scatter over impurities and degrade. So you generate, to conserve momentum, you generate two different population in the so-called acoustic branches, so the longitudinal and transversal acoustic branches. And then you have more and more degradation to get to a new equilibrium distribution of phonons. And since this is proportional to energy, the lifetime, the inverse of gamma, is increased as the energy decrease. And finally, you get to this new equilibrium distribution of phonons inside the crystal, which is exactly the temperature of the crystal. And you get, in this way, a temperature increase. So we can, in some ways, sketch this. You have a crystal or a solid with a stable temperature, so you have a stable distribution of phonons in energy, and then you have the interacting radiation, which produce an out of equilibrium distribution of phonons, which is typically quite narrow, quite sharp, and then through degradation, phonons decrease and decrease more and more their energy, and then eventually you get to a final new distribution, which is the new temperature of the crystal. Basically, the idea of cryogenic detectors is that measuring this temperature increase, this delta T, you are able to measure the energy. This, which is, I think, obvious. The number and the energy of the generated phonons is proportional to the energy of the impinging particle and the released energy in the absorber. So the larger the temperature rise, the larger the released energy. Basically, here is where your sensor is really acting. I was saying that even though this distribution contains a lot of information of the time of radiation and interaction, it's very difficult to profit from this information, because when you start to be sensitive, most of the information has been averaged away by reflection and decreasing of energy. So here is where your typically phonon sensor are operating. This is finally the sketch of a cryogenic detector. So you have an absorber that it's in some way thermally coupled with a heat sink, with a bath that is keeping to a stable energy, to a stable temperature, some heat reservoir that keep your crystal stable in temperature. This coupling is very relevant to the working of this device, because if this is too strong, you are not able, the energy flows to the sink before you're able to measure it. So it has to be in some way a weak thermal coupling, but cannot be too weak, otherwise you get a very long signal and it's difficult to integrate the energy. And of course you have to have a sensor. This is a picture of one of the, I think this is one of the Quarry prototypes. So this is a 5 by 5 by 5 centimeter cube of tellurium dioxide, and you see one of the phonon sensors that are used in the Quarry experiment. But it's just to show you how it's a possible configuration. In this configuration, the crystal is held by Teflon supports that have a very poor thermal conductance. So the real, let's say, connection to the heat sink are the readout wires, the golden wires that take out the readout signal. So if they're in this configuration, the coupling is good enough that you have time to see a pulse evolution. So, okay, in this kind of configuration, the real relevant parameter in a simplified model of to be able to measure the energy is the heat capacity. And the thermal conductance to the bud enables to temperature recover. So you have a signal amplitude which is given by the energy over the heat capacity of the material, and you have a relaxation time that is given by this heat capacity and the coupling, which gives you that, of course, dielectric and diamagnetic materials are preferred because at extremely low temperature, you don't have the component of the specific heat that goes proportional to T, which is the electron part of the by law. And with diamagnetic materials, it's even worse because at low temperature, you have that the heat capacity increase as 1 over T. So using diamagnetic material is very inconvenient for this. But still with this limitation, you have a wide choice of material, which is one also of the very relevant reason why people do use this kind of detectors. And this is how you expect, what you expect to see from your temperature for your phonon sensor. You have a radiation interaction, an alpha decay or an electron interacting in your crystal, and you have energy jump here, which is proportional to the, sorry, a temperature jump here, which is proportional to the energy, and then a decrease, an exponential decrease with this time constant, which is C over G. This is a particular example that comes from this kind of detector, in which you see that the time scale is extremely slow. In these detectors, which are order kilogram of mass, the time evolution of the pulse is in the order of seconds of decay time. This means that this kind of detector cannot be used for observing any kind of process which has a high rate. So basically, rare events are the target of this kind of detector. This is kind of extreme, of course. If you use a much, much smaller absorber mass, C becomes extremely small, and playing with C and G, you can get much smaller, much faster decay time, but still in the range of tens of milliseconds. So still compared to, for example, light emission, this kind of detectors are not suitable for high rate processes. And this is one of the reasons why large cryogenic detectors, what people call from usually or sometimes macrobolometers, are used basically only in underground location, because the cosmic ray flow kills your capability of distinguishing any particle interaction, because you're completely blind due to the too high rate of muons. So here we get to one very important issue, is that the temperature that you need to operate this detector is extremely small. You have heard about cryogenics in the tens of hundreds of Kelvin, but here we have to go to really approach the absolute zero, because the temperature range of operation of this detector is, let's say, roughly between 100 and 10 millikelvin, but more to the side of the 10 millikelvin. And I think the reason is very simple. If you have 1 gram of of tellurium dioxide, a 1 keV interaction produces an increase roughly of 10 to the minus 16 Kelvin, so something very difficult to measure on one side and something very small compared to the thermal excitation due just to the temperature, to the phonon distribution due to temperature. But if you go to 10 millikelvin, you have something in the order of the 10 to 1 microkelvin excitation, which is in some way easy to measure, and the thermal excitation are almost negligible with respect to this value. So at this temperature, you have the possibility to measure with 1 kilogram device, but in this case 1 gram, but even with larger, yeah, I think this number is for 1 kilogram, not for 1 gram. The temperature increase for 1 gram is for sure larger, but anyway, you have the possibility of measuring the interaction of 1 keV particle in one of this device. So a short intermediate summary of what we have seen so far. The advantage of this kind of detectors is that they provide natural, in some way, an extremely good energy resolution. And on the other real advantage is that you have a wide choice of materials for the energy absorber, which looking to many different physics processes can be very useful. You can even get multi-target materials, like tellurium dioxide we observed. You have a very heavy material, tellurium, which is 150 something in atomic mass, and you have oxygen, so a much lighter material. On the other side, there are also suboptimal performance, the fact that the signals are extremely slow, depending, of course, on the sensor and on the mass, so on the heat capacity of the detector. They need to work at extremely low temperature, which means that you have to use some kind of apparatus of machine that provides this low temperature detector that usually are objects that are kind of complicated. In principle, in a pure bolometer, it's not easy to have radiation identification information, and this also is an issue because if you are looking, if the type of radiation is a signature of your process, having no radiation identification feature is a limitation, and in some way can be difficult to scale at very large masses. I will comment on this at the end, but basically, since you need all this cryogenic infrastructure, getting to many multi-ton mass, it's extremely difficult for this technology. So it's a technology that is very appealing, but for specific kind of research. Quanto devo andare avanti prima della pausa? But I stop after this. So let me say a few words about how you get to this temperature. Reaching millikelvin temperature is not obvious in some way. So the kind of machine you use to get to this temperature is basically reduced to one kind of device that are dilution refrigerators. In the last century, many developments have been performed in cryogenic physics, and many ways of lowering temperature have been explored, but dilution units have been the real step forward with respect to what people was using before, like adiabatic demagnetization systems and what is called Pomeranian cooling, because this kind of device not only allow you to reach extremely low temperature, but also to maintain stable over time this temperature. So this completely changed the field of low temperature physics, but also opened the way to a wide range of application. And nowadays, this kind of machine are also used for what is called basically quantum computing. So the so-called qubits or many kind of this qubits have to work at extremely low temperature. So the technology was further boosted by a number of different applications far away also from base research that was the basic application. And nowadays there is a bunch and an increasing number of companies that offer you dilution refrigerator that you can buy basically on catalog if you have your own $500,000. You don't know how to spend it. So the original idea was developed in the 50s, basically by London, but then in the Leiden physics department, there were the real first application and development of practical working devices. And at the end of the 60s, Oxford Instruments was the first company to produce commercially, to offer commercially one of this device. The concept, it's in some way not super simple. Basically, what happens usually in cryogenic physics is you cool down by steps. So usually you have a 4 Kelvin stage, which is provided typically by liquid helium bath, for example. The temperature of liquefied helium is 4.2 Kelvin. Then you need even colder stage, the so-called 1K stage, which can be obtained, for example, pumping a liquid helium bath, so forcing evaporation, removing latent heat from the bath and cooling and reducing further the temperature. And then you have a bunch of stages which are all focused to this object, the so-called mixing chamber, where there is a mixture of helium-3 and helium-4 that have specific properties which bring to the happening of the dilution, that is the physical process that eventually cools down the temperature, removes heat or takes away heat to bring you to the base temperature, which this kind of device you can reach easily temperatures in the few millikelvin range. So it's extremely powerful device. Just a few words about a very important quantity if you are dealing with low temperature physics, which is enthalpy. Enthalpy was some kind of thing which, when I studied in university, I thought this is the last time I will ever heard about enthalpy, but eventually I ended up doing a calculation with enthalpy because it's a state function, as you know, which is related to the internal energy and just pressure and volume. And this is a very convenient function to estimate the energy needed for a specific variation of a material. And if you have, for example, a solid material in which this quantity is kind of constant over temperature, this allows easily to do calculation. I will not go too much into the details, but this is important because it tells you a little bit about how allows us to do some easy estimation on how much cold material you need to cool down a solid. This is a table of the estimate of how much cryogenic fluid, the most common cryogenic fluids are liquid nitrogen and liquid helium, so how much cryogenic fluid you need if you want to cool something from room temperature to the nitrogen temperature, so 77 Kelvin, and then from 77 to 4.2, which is the liquid helium temperature. And then what about if you skip the nitrogen and you just use liquid helium to cool down from room temperature to 4 Kelvin? And what you see is that if you consider only the evaporation, the latent heat, you need some 1 liter per kilogram to complete this temperature step. But if you profit from also all the internal energy, so you don't just let the helium of the nitrogen evaporate in contact with your material, but you profit from the expansion and the temperature of the evaporating gas of nitrogen. So you use, you maximize the use of all the internal energy. You end up with much less liquid nitrogen needed to cool 1 kilogram of aluminum, copper, of stainless steel. And as you see, using just helium is very inconvenient because you burn a lot of liquid helium, but using nitrogen to 77 and then helium for the step from 77 to 4.2 is extremely convenient. This is just to give you an idea because, of course, when you start with whatever object you want to cool down, you start from room temperature. So usually you have to step down to first to 77 and then to 4.2. So any dilution refrigerator have a temperature stage at 4.2, and historically this was obtained just with a liquid helium bath. This adds the advantage that you have this, you can have a large liquid helium bath that keeps the temperature of your 4.2 stage extremely stable. Sometimes you need to keep your 4.2 Kelvin bath stable, also an external bath at 77 Kelvin, so a liquid nitrogen bath or a cold gaseous nitrogen jacket. But the disadvantage of this is that liquid helium evaporates over time. So with some, you have to account for some downtime, that is the refill of the liquid helium bath. In more recent years, the liquid helium bath was basically replaced by this kind of cold head, what people call pulse tubes. There are cryocoolers which have a basically closed thermal cycle performed with gaseous helium with a thermal expansion. This part of the so-called tube where you have this expansion of the helium gas, and this closed circuit you are able to provide the two-stage. This is the two-stage, one around 40 Kelvin and one around 4 Kelvin. This is a huge advantage in terms of lifetime and duty cycle because you don't need to do the helium bath refill, and this has much less problems like leaks, which are very common when you have a liquid helium bath, and you can have a very stable cooling power over time. Now the technology is improved so much that you can get some 2.5 watts at 4 Kelvin, which is a quite large cooling power. Of course, you have some drawbacks. I think that the most relevant is that this object induces vibrations. You have a strong, very strong expansion in the tube, which induce oscillation in the system and induce vibration in your system. As we were saying before, the goal can be to measure energy quantities in your cryogenic detectors as low as a fraction of a keV, tenths of electron volt. How much vibration do you need to induce through friction, for example, an energy dissipation of 10 to the minus 19 joule on your detector? Not that much. So dealing with can have downside, and this is why people develop a number of systems to decouple vibration induced by this machine, and also active noise cancellation system just to allow the operation of cryogenic detectors. Anyway, you have to have a 4 Kelvin stage, and then you have the dilution refrigerator. In the system with a liquid bath, you have what people used to call wet dilution units, in which you have the 1 kpot stage, as I was mentioning, and then the dilution system with the two phases, the helium-4 and helium-3, which I will come back in a second. In dry dilution units, so without liquid helium bath, the 1K pot is replaced by extra heat exchange on the system. Let's say, once you understand the details also of the dilution of the properties of helium-3 and helium-4, building a dilution unit is rather simple. You buy helium-3 and helium-4 in the proper quantities, you set up your pumping line. What is difficult is what you see here, this heat exchanger, because the system has to be stable over time. So this means that the cooling power plus the work of the pumps plus the downgoing warm helium-3 and the upgoing cold helium-3 exchanging heat among them have to generate a stable infrastructure. So the real tricky part is to balance all the different heat load and contribution to have something which is stable over time. So what is really dilution? What happens? So basically what you do, you profit from properties of the mixture of helium-3 and helium-4. Helium-3 and helium-4 have very different properties at low temperatures because they behave as, let's say, particles of 0 spin or 1/2 spin, so with different statistics. And basically, when you get at extremely low temperature, the quantum coherence between a large number of these atoms became a relevant process. And what happened at very low temperature is that at some point you have that helium-4 became superfluid while helium-3 not, because helium-3 became superfluid at extremely low temperature, few below 3 millikelvin, and so in the higher temperature part you have the normal behavior of helium-3, helium-4 mixed as gas or liquids. But when you get below temperature of the order of, let's say, 600 millikelvin or so, fraction of a Kelvin, you start to have a pure helium. So basically what happens is the two phases separate. The helium-3 and the helium-4 separate. The helium-4 that is heavier goes below and the helium-3 goes above. But what happens, depending on the different, let's say, statistical distribution of this liquids, is that while helium-3 end up in a completely pure helium-3 phase, in the helium-4 there are intermediate levels available which induce a diffusion of helium-3 inside the helium-4. So in this phase you have something like 6% of diffused helium-3 inside the liquid helium-4. And this is what you use to, I think I skipped one slide. This is what you use to induce dilution. Basically, you end up with a pipe getting into the helium-4 phase with the diffused helium-3, and you pump over this lower liquid. So in this pipe, you reach a level which is at a temperature of around 600 millikelvin. At 600 millikelvin, the ratio between the latent heat of helium-2 and helium-4 is very unbalanced. It's much, much larger for helium-3. So when you pump, you basically remove only helium-3. So from the helium-4 phase, you pump away a mixture of helium-3 or helium-4, which is some 99% helium-3 at that temperature. So what happens here is that to keep the ratio constant, helium-3 dilutes into the helium-4, repopulating the available levels that were emptied by the pumping. So this operation of this action of diluting is an energy consuming operation, and so the dilution is what eats the heat to bring you to the millikelvin temperature. Thanks to this process, thanks to what is happening, thanks to the dilution, you are able to cool nowadays even large masses to extremely low temperature. Of course, the dilution unit design requires a lot of know-how. This is what I was showing you before, the heat exchanger. So in these pipes you see here, there are two separate lines counterflowing. The cold helium 3 that is pumped away from here through the steel, and the counterflowing warm helium 3 that is downgoing and gets eventually into the mixing chamber where the dilution happens. So you get optimizing this heat exchanger, you get to a stable condition in which you can keep your device or material that you want to test or experiment at millikelvin temperatures in stable condition over time. So this is the Quore dilution refrigerator with all the different stages. At the time, this was completely customly built because it was, and it's still the largest dilution refrigerator ever built. This has an experimental volume that is larger than a cubic meter. So we have something like 1 cubic meter at 7 millikelvin eventually. So basically, this cryostat opened the way to the fact that now you can think to have ton-scale cryogenic projects, and it showed that you can work steadily over time. Since 2017, this cryostat is working steadily and was never warmed up to room temperature again. So it was able to collect something roughly, it's approaching 2 ton year of exposure. So, and again, as I told you, the quantum computing community is boosting even more the technology of dilution refrigerator. So starting from this experience, now there are many companies which are offering on their catalog dilution unit which have a cooling power comparable or even greater than the Quore cooling power. So nowadays, even though cryogenic technology is in some way very complicated, there have been a lot of developments that allow you to buy a dilution refrigerator which cools down to 10 millikelvin just pressing a button in some way. So it's a complicated technology, but is affordable nowadays. So I think maybe before I get to phonon sensor, we have a break for
short break con possible questions.
If there is any.
No curiosities? Yes.
Thanks. I was asking hello, yeah. Could you please explain a bit more on the pulse tube and how does it work?
Okay, basically there are a number nowadays of cryo coolers. Basically all of these are based on some kind of helium gas thermal cycles. So you have compression and expansion of helium gas under specific conditions that allow the reduction of temperature. The reason why pulse tubes, can I go back? Oops. Yeah, the reason why pulse tubes became so popular is that there is no mechanical moving part at cold temperature. One other device that is very popular for cryocooler is, one other thermal cycle is what is called Gifford-McMahon cycle, in which the compression expansion is done with a piston that goes to low temperature. So you have always a moving part that has to be at low temperature, and which also induce a lot more of vibration because you have really a bumping piston all the time. The advantage of pulse tube is that you have this, it's actually a double stage system, so you have two expansion volume, but the basic idea is that you have an expansion volume, the tube, and a rotating valve, which is connected, this part here, which is connected to the high pressure and low pressure. So the rotation of the valve opened the communication of the tube to the high pressure side and the low pressure side. So basically what you end up having is a pulsed expansion into this tube, which is then pumped away by the compressor and re-injected. And this kind of expansion through a specific orifice, which allows expansion through a compression, a dilatation after the orifice in this tube, is the part of the thermal cycle that guarantees the temperature lowering. Also in this case, most of the technology is about the thermalization of the double stage and the fact that you inject in the second tube gas that is pre-cooled on the first stage, and this allow further cooling. So with single stage pulse tubes, you get to temperatures which are in the 40 to 30 Kelvin range, maybe slightly lower, but with double stage, you can reach something of the order of 1.5 Kelvin, so depending on the cooling power that you need. So, but this is now really established technology, so this is commercial stuff. The biggest producer is Cryomec, but there are a bunch of others which are now producing this kind of device, and you just buy on the catalog. So this is really, really plug and play. You just put it there, press the button, and this goes.
Yeah, I was just curious, how does it work? Okay, thanks. I have another small question. If you go to any cryostat picture, so there are some plates, and I don't know, if you go to the previous picture, previous slide. Yes, so is there any function of the disc-like plates or?
So basically, one thing I didn't maybe mention, but is very important, is that over the dilution unit, this is just the lower part of the dilution unit, but if you look into this picture, this is a full dilution unit. Probably this upper one is the room temperature plate. So as you have plates at decreasing temperature, you have to be into vacuum. Otherwise, the conductance will kill your cooling device. And what you usually have is a thermal shield to reduce the contribution of thermal irradiation. You know that thermal irradiation goes through with the Boltzmann law, so the Stephen-Boltzmann radiation, you get something that is proportional to the difference of the temperature to the fourth power. So having a step, if you just have a jump between room temperature and, for example, 4 Kelvin, it's a huge power dissipation. But if you have an intermediate shield, thermal shield here, which is at 77, or in this case, this is pulse tube, so this is around 40 Kelvin, this reduce enormously the power load to the 4K stage. Yeah. And since the lower you go, the amount of power you're able to, the heat leak that you are able to support at colder stage is much, much smaller. It's extremely more convenient to have a stage at a higher temperature that absorb. In the 40 Kelvin stage, you have tens of watts of cooling power. At the 4 Kelvin stage, you have order watts of cooling power. Here at the 600, you are in the range of tens of milliwatts. At the 50K, you're probably around 1 milliwatt or below, but in the base temperature stage, you are in the order of microwatts or fraction of a microwatt. So, of course, this is crucial to have all this stage to get very small irradiation, thermal irradiation on the colder stages.
Okay, thanks.
For every plate, there is a vessel at the end. It's like onions. Other questions? Or we go on? Want to go
Okay. Let's try to go on. So, as I mentioned at the beginning, the real crucial technological part of this kind of device is the phonon sensor. So phonon sensors are really the part in which you do measure the energy. And basically, a phonon sensor is a device that collects phonons and generates or modulates an electrical signal or that is basically proportional to the energy contained in the phonons. So if one phonon-mediated device or detector is operated as a perfect calorimeter, basically what you have is a thermometer. You are measuring the temperature of, first of all, of the phonon device, but basically of whatever is coupled to the phonon device or the absorber. In practical device, there are a couple of sensors that are the ones that are really extensively employed, and these are semiconductor thermistors and transition edge sensors. There are nowadays a lot of other technologies that have been developed. I think the most used is this KID technology, kinetic inductance detectors. I will not have time to mention this and the magnetic microcalorimeters, but just to tell you that there are also other kind of device that can, for which you can profit of particular properties. One, let's say, very important properties, which is already, I think, well used in kids, is multiplexing that can be very relevant if you have a very large number of detectors. But anyway, now I will say some words on these first two, and some of this can be extended to the other kind of phonon sensor. So, semiconductor sensor, so again, we are speaking of something which is acting as a thermometer, and these are semiconductors that are doped to get close to the metal to insulator transition, and this kind of semiconductors at low temperatures, their resistivity is expressed by this formula here. So you see that there is an exponential correlation between the temperature variation and the resistivities. And this, at this temperature, you have this very specific conduction regime, which is called variable range hopping, which basically is a conduction regime in which your electron do not reach the conduction band, but gets very near to it and then move to a nearby site via tunneling. So in this conduction regime, you have a very steep correlation between resistivity and temperature, and through these two parameters, which basically depend on the doping level. So depending on how much you dope your semiconductor, you get different T0 and R0, and you tune in some way the sensitivity of your device. I think there are basically two types of semiconductor thermistors that are widely used. One is the so-called neutron transmutation doped germanium thermistor. This NTD means it's basically the technology that is used to generate this doping that brings it near the metal to insulator transition. And this is done exposing the germanium samples to a extremely strong neutron beam, typically in a nuclear reactor. And through the neutron capture and the following decays, you produce P and N doping inside the thermistor, and you can in some way tune, if you know well enough your neutron source, your reactor, you can tune very well the dose you inject into this thermistor, and tune in some way the R0 and T0 parameters to get to the sensitivity that is needed for your kind of device. The other approach is instead silicon implanted thermistors, in which the doping is done through implantation. These are more related to microelectronic technologies, and again you can have a very good implantation level and control and get very sensitive sensor. I believe that these silicon implanted are mostly used in microcalorimeters, so extremely small calorimeters, but in some way both technologies are reliable. What you get is a readout of the tension in this kind of sensor, and this tension you read is proportional to the temperature variation, or basically the resistance variation is induced by the temperature variation. The advantage of this kind of device is they are sensitive over a very large range of temperatures. You have typically very high impedance. The resistivity or the resistance of this device is in the megaohm to gigaohm scale, so you can use standard type of electronics. You don't need any special readout device, and of course you have to deal with some kind of noise sources. The advantage of this kind of devices is that they're extremely easy to handle, and they are usually coupled with the absorber through some kind of epoxy or glue, so they're basically glued on your absorbent material, so you can stick your NTD or your semiconductor thermistor on the material you like most. And they are typically, for this reason, they are not very sensitive to a thermal phonons. This is because the glue or the epoxy that you use to couple the two objects, the absorber and the sensor, is typically an amorphous, which acts a little bit as a low-pass filter for phonons. So very high frequency phonons are not collected, and this in some way reduce a little bit your sensitivity of the first part of the interaction. But overall are extremely suitable device, especially if you're interested in a wide energy range to be measured. The other kind of device is instead a transition edge sensor, so basically superconducting films which are kept in the transition. So As you know, the superconducting transition of a superconductor is not a step function, but is some smooth decrease from the fixed value of resistivity basically to zero resistivity. So if you are able to tune the temperature of your sensor to stay in the linear part of this superconducting transition, to very small temperature variation correspond very large resistance variation. Just to give you an idea, if you try to parameterize the sensitivity of a semiconductor thermistor with respect to TES, there is some factor of 100 in sensitivity more for transition edge sensors. So these are extremely more sensitive. Of course, as usual, you have to pay a price for this, and the first price is that the resistance you have to measure, the variation is extremely small in the milliohm range, and so you need some dedicated readout. In particular, you basically are forced to use squids to read out the signal of this kind of sensor. And of course, the signal to noise ratio is much higher in this kind of device. And the other disadvantage in some ways that you cannot, let's say, not easily glue the sensor on the absorber. You need to deposit a superconducting film on your absorber. So this is subject to the chemistry or mechanical characteristics of the different absorbers with respect to the sputtered or evaporated superconductor. The most used actually in this kind of devices in the, let's say, low part of the temperature range, so around 10 millikelvin, is tungsten. Metal tungsten has a critical temperature of 15 millikelvin, so if you deposit a superconducting film, you will have a tuning of the critical temperature as you are coupled to another material, but basically you have something which is in the range where you maximize the temperature effect. And of course, this part, the deposition, is a tricky operation and is not always extremely reproducible, so you may need to characterize each individual deposition to be sure that you are in the proper temperature range. This is an example of a tungsten transition edge sensor. Again, you need the squid readout to measure such a small variation of the resistance, and you have specific noise that is related of this kind of device, but basically at a very small critical temperature and its capacity, you have a very small noise and optimal energy resolution. So it's a very efficient device. And the kind of variation you deal with the deposition in the absorber of the order of 1 keV, you have an increase of the temperature in the TES in the microkelvin range, and as I said before, you have a resistance change in the millikelvin range. Which is the main downside of these detectors? Well, the main downside is that the dynamic range is extremely small. The limitation is the fact that when your temperature variation exceeds the transition, as you see, basically you exceed the dynamic range. The resistance does not vary anymore or vary extremely small, so it's difficult to measure with the temperature. And what you get in terms of signal, this in red, you see a nice response pulse that you get when you're fully contained in the superconducting transition, but when you exceed, you end up with something like a saturated pulse. So whichever pulse exceed the transition range is cut at this level, then depending on the energy will have a decay time that starts later on. So the saturation can be smaller or shorter, shorter or longer depending on how much you exceed. So is this a complete limitation? It is not, because template-based pulse reconstruction allow to extend the dynamic range quite a bit. So this is an example from the CREST experiment. Here you have a saturated pulse in blue, and this is the template, the reconstructed pulse you extract from the linear part of the temperature radiation, and you scale to fit the rise and the decay. So depending on the energy range, the rise will be very similar, but the decay will be far away, and the high of the pulse will increase correspondingly. And this technique, even though it is not so accurate as a spectrum you can get with germanium NTD, for example, allows you to reconstruct and extend the dynamic range quite a bit. If you have a energy threshold, the dynamic range and let's say 100 keV, you can, with this technique, extract the spectrum to several MeV with appreciable reconstruction of the energy, and you can reconstruct easily the background structure you have in this energy range. So it's not perfect, but it's quite quite working. In some way, if you have to build your own detector and choose which sensor, this kind of sensor, you will choose it if you have a process which is in the linear part of the transition. So it's very small, and you need a lot of sensitivity at very small energy. For example, measuring dark matter at very low energies. And you can use the reconstructed energy spectrum just to check the different components of the background and so on. Oops, sorry. So, again, as usual, you will choose your favorite or suitable temperature sensor depending on the kind of physics process you're going to search for. In general, there are few also background types that are characteristic of this kind of detector. I think you heard this many times these days, but of course any kind of process has its own specific background, and depending on what you have to measure, you have to fight with that specific background. But as was anticipated before, these detectors are basically operating in vacuum. So this has one advantage: you have nothing around the detector, but the disadvantage is that there is no veto effect or fiducialization of the volume of the detector you put in place easily. So your detector is exposed to whatever comes out from the surface facing the detector and can travel through vacuum and hit your detector. So a typical background kind is what people call degraded alpha particles. So if you have an alpha particle that is emitted on one, this is an example with a tellurium oxide crystal, it's emitted near the surface and escape and hit the other nearby tellurium oxide crystal. If you do a coincidence analysis of these two events, you can reconstruct the full energy of the original event and eventually understand that that was 5.4 MeV was a polonium-210 alpha peak. But if one of the two surface that is hit by the alpha is a non-active surface, like the copper structure here in the sketch, then you get an event which has a random energy between the Q value of this process and 0, depending on how much part is left in the two sides. So this kind of background is very typical of this kind of detectors. this is just a little bit more of details on this. The alpha particle generated near the surface of a detector will release only a part of its energy before escaping. And so if you hit another material which is non-active, you get something that is a fraction of the energy of the process, and which makes very difficult to reconstruct the origin of this background. And you can get very annoying background in some way. One example is if you have a particle which is exactly on the surface of a non-active material facing your detector. If you have the alpha hitting the detector and the nuclear recoil in the non-active, this is easy to understand, but if you have the alpha in the material and the nuclear recoil hitting your detector, then you get a background at low energy, which is in some way very similar to what you expect from a dark matter interaction, and this is very dangerous for a dark matter experiment. You have other regions, other kind of separation or fractioning of the energies that can disturb double beta decay. Just to give you a couple of physics process you can look at, but depending on the physics process, this can be an annoying, an extremely dangerous background. This is an example from one of the quarry prototypes in which you can extrapolate from this region in which you expect basically no background, and instead you find a flat background which extends up to the alpha peaks, which is the degraded alpha background, which has also contributed to the neutrinoless double beta decay region, and so it's limiting your sensitivity to that kind of process. So this is basically why people over time develop also what is called sometimes composite bolometers or double readout bolometers that are bolometers in which one tries to boost the background discrimination or the particle identification capability, adding a new readout channel. So there are two main channels that have been explored so far, the heat plus light and heat plus ionization. So in the heat plus ionization, you have a semiconductor operated as a bolometer, so you have the current correction plates, which collect the ions and the electrons inside the diode. And on the other side, you produce phonons that are collected by your phonon sensor. The other option is what is called scintillating bolometers, in which your absorber crystal is also a scintillator. So when you have a particle interaction, you produce again phonons that are read by a phonon sensor, and you produce light that can be read by a light detector. Note that this kind of device are still operated at ultra-cryogenic temperatures in the 10 millikelvin range. So you cannot just place a phototube here and try to read your light emission, because at those temperatures there is basically no chance that you can extract electrons from the photocathode, and there is no way to read this light with a, let's say, commercial or standard light detection device. And this is why people develop bolometric light detector, cryogenic light detector, which are basically, again, some kind of cryogenic detector which is used to collect the light escaping from this detector, which is the general idea. This is an example which comes from this Cupid-Mo prototype. So lithium molybdate detector operate as lithium molybdate crystal operate as scintillating bolometers, and basically if you cross the reading of the heat channel versus the light channel, you get out with a scatter plot which identifies very well the different kind of radiation. So you can separate the alpha band very well from the beta gamma band. This is Cupid-Mo is a project looking for neutrino-less double beta decay. So what is relevant is that you don't have any more this continuous background in the at the Q beta beta energy. So using the cross information from the heat that you typically keep as the measurement of the energy, as it gives you a very accurate readout of the energy, and the light that gives you instead the contribution, the information on the radiation type, you can use this to in some way boost the information you can extract from your detector. Let me mention also that for this kind of device, the fact that the electrons and the ion are collected by special grids on the two faces allows you also to do some volume fiducialization. So you can profit also from this double readout to tag and exclude surface events from your let's say data, and this also it's a way of reducing further the background for this kind of detectors. In some way, the limitation here is that you are basically limited to silicon and germanium because you need to operate in diode mode, while for scintillating detectors there is a quite large variety of materials which you can also get, for example, doping some specific materials with some light emitter and so on. So the choice of crystal that you can use for scintillating cryogenic detectors is much larger than the one that you can use for the diodes, let's say. So this is basically my general introduction about cryogenic detectors. There is a lot of information we didn't went into. There are different, for example, readout mode in some way. In some readout mode, you integrate the full energy, in other the flow. But basically, most of the information to understand this kind of device. Few words about the physics application. So a couple experiments that are here at the Gran Sasso laboratory. The Cuore experiment, it's relevant for this discussion because the Cuore experiment, I anticipated this speaking about the cryostat, set a new standard for what concerned the mass you can cool to low temperature. Before Cuore, the largest mass ever cooled to 10 millikelvin was in the range of some tens of kilograms, 40 kilograms or less. There were attempts in completely different fields like resonant bar for gravitational waves search, in which there were attempts to cool larger mass to cryogenic temperatures, but this never went below a couple of 100 millikelvin. So at few millikelvin, there was no detector exceeding the tens of kilos, and that was considered some way a limit of the technology. Cuore is about 1 ton of material. It was developed by the Cuore collaboration in partnership with some companies, and basically from the point of view of the mass reachable with this kind of technology, Cuore demonstrated the feasibility of ton-scale experiment employing cryogenic calorimeters, in particular in this case for the search of neutrino-less double beta decay, and basically set a new benchmark for a number of new experiments which are now proposed all around the world, aiming to reach similar or even larger masses with cryogenic technology. And for this kind of research, so neutrino-less double beta decay, low temperature detectors proved to be really competitive with the best actors in the field in terms of performance, scalability, and sensitivities. And also, Quare proved that you can run such a complex object in reasonably steady condition for a long time. I anticipate Quare was cooled down to base temperature in 2017, and there was an intermediate thermal cycle to some 50 Kelvin maybe, but apart from that, it was never warmed up again. So it's extremely stable and allows to run for a long time this kind of detector, which for large exposure is one of the critical issues. And also, of course, the granularity of such a detector offers a very interesting tool for specific kind of signature and for rejecting specific backgrounds. So one of the real advantage of such a detector is that you can profit from the 988 detectors. Actually, one other relevant features was that the reproducibility in delivering working detector was extremely good. So Quare lost in his thermal cycle something like 4 detectors over 988, which is really an extremely good number for this kind of application. On the opposite side, in some way of the performance, we have the CREST detector, which is a dark matter searching experiment, which use, I don't know if I mentioned, but Quare use NTD germanium phonon sensors. CREST use tungsten films deposited on a calcium tungstate crystals to search for dark matter. And in recent years, CREST used some 24 grams detector, so very small if you compare to here is the calcium tungstate detector is 2 by 2 by 1 centimeter compared to the 5 by 5 by 5 cubic centimeters of the almost 1 kilogram mass Quare detector. But with this small detector, so reducing in some way the heat capacity, CREST was able to reach an energy threshold in the order of 30 electron volt, which is an unprecedented low energy threshold in the field, and allowed CREST to set very important limits on extremely light dark matter candidates. So apart from the physics case, CREST set a new benchmark for energy threshold in cryogenic detectors, and in the future we can probably aim to reach threshold in the 10 electron volt range, and these are already the target for a number of new experiments with masses in the order of 10 or few tens of grams, aiming of different physics process. Low temperature detector technology is led by this kind of sensor right now, and on the other side, the complexity and the small mass of the individual CREST module is a strong limitation for the exposure. You have heard in these days that cryogenic liquid xenon, liquid argon can reach multi-ton masses for dark matter search. So in the high mass dark matter, it's very difficult to compete with the exposure of these experiments, but in the light dark matter range, on the other side, it's very difficult for this large cryogenic liquid-based experiment, dual TPCs, to compete with the CREST thresholds. And already now, CREST-like TES are now being used in many different projects in the neutrino physics and in the dark matter search. Just to conclude, there are a number of projects already running or projected for the future. One it will be here, it's Cupid, it's the upgrade of Quare with scintillating detector, so adding scintillation features using lithium molybdate crystal to Quare to boost the Quare sensitivity. One other very interesting project is Nucleus, that is using the CREST technology to measure neutrino nucleus coherent scattering, and again can profit for this kind of detection, the low threshold is the crucial parameter. So using very small detectors and aiming at tens of electron volts in threshold, they can really explore deeply this channel, and there are a number of physics cases within reach of this kind of detectors. There is already a number of dark matter experiments which are using phonon plus ionization channels, like Edelweiss at Modane in France, and Super CDMS that will be installed at SoUP. And this is another proposal for the future, that is to use neutrino scattering over nuclei to measure supernova neutrinos, and solid material through this coherent neutrino scattering can be a strong boost of the supernova neutrino signal. So it's very interesting also, this one. There is the Cosinus project, which is again scintillating detectors to search for dark matter with a sodium iodine target and so on. There are a real number of projects which were developed in the last few years. I will not go further. This last few slides were just to give you the taste of the fact that there is a lot of application in which this technology is the right one that you may want to use. There are many other applications in which there are other technologies that are preferable. So again, the starting point is always the science channel you want to explore, and then find a suitable technology for that. Okay.
Thank you, Paolo. Questions?
Thank you. I'm Matteo from Sapienza, and I was curious about the what was it? The neutron transmutation doping, the semiconductor detectors, and about specifically because I imagine that using neutron irradiation to dope those detectors would create discontinuities in the crystal, and would that be harmful or helpful for like phonon absorption, for example?
I'm not. What is it? Okay. Anyway, so the issue with neutron transmutation doping is you expose this sample to a strong neutron flux. What you get is basically mostly neutron capture. So you produce some specific isotope that decaying. So you typically, in case of germanium, you produce germanium isotope with a higher number of neutrons, which eventually undergo beta decay or electron capture and produce your dopant. The downside of the production is usually that you produce this doping, and you produce a number of typically short-lived isotopes which you don't care about your doping, but which make your sample very hot in terms of radioactivity at the beginning. So this kind of preparation is not just you go today, you expose your sample to the reactor and then come back home. You have some cooling time that usually is in the several months scale or 1 year scale. So that is the real issue. I don't think you produce many or too many dislocation in the germ. At least not that I know. It's the real issue is the amount of radioactive material that you produce that make your sample very hot and make your sample very contaminated. If in germanium, these are, to my knowledge, all short-lived. So this gives you the fact that after 1 year of cooling down, your device is ready to be used as a thermometer. in reality, if you have some residual contamination inside the thermistor, what you get is that the signal which is generated inside the thermistor has a completely different shape of respect to the one that is generated in the absorbent, because the heat capacity of the thermistor is very, very small. So you have something like, with respect to the time evolution of a standard pulse, you have some spike-like pulses, which are many people using this kind of thermistor have some population of spikes which are attributed to residual contamination in the NTDs or semiconductor devices.
Other questions? Time for lunch?
People is waiting for lunch.
Okay, so let's close the session here and let's have lunch.